Of course, that would open on the other monitor. All right. We are in day 14 of Advent of Code. This makes 2 weeks that we've been streaming every day for Advent of Code. That is a lot. It's a lot of days. I think that puts us, what, more than halfway through? Oops, that's not, nobody saw that. It's fine. Definitely nothing interesting happening there, for sure. 2021. Rust. Day 13. Will today be the day that I build the cargo generate script? Probably not, but you know, maybe. Hey Derek, how's it going? I'm feeling good. My desk isn't clean right now because I just moved my extension cables and all of the wires off of my desk to mount them under the desk, and I'm happy about that. But my desk is not clean, so it feels like there's more space. There's still a bunch of stuff. Move this to the left. So let's get rid of all the steps that I had from yesterday. I guess I didn't really improve the situation from yesterday. Let's take a look at that first, actually. Let's talk a little bit, tiny bit about day 13. Let me blow this up. So I started writing them all out into files in an attempt to debug where I was going wrong, because the output that I am getting is this monstrosity, which I don't believe is the correct output. However, I found it really interesting that basically it works for the test input, but not for the actual input. So I guess the only thing that I'm down to is it could possibly be the way I'm parsing the input, maybe. Cable management, love that. Need to figure out what to do with the mess of cables that go into the mic setup, the USB switch, and the MacBook, and the computers, and the monitors, and the phones, and the iPads, and a lot of wires on the desk. Either the Stream Deck has a wire, the headphones have a wire, the mics have wires, everything's wired. But so yeah, I wrote this to file function. I started writing it out to files. That didn't really help me because we don't have anything to compare it to, really. So to debug this, what I'm actually going to have to do in the end, I believe, is write the other implementation. Hope I write the other implementation, the Hashmap one, correctly, so that I get the right output, and then log out every dot that's supposed to be in every step, and then compare that and see where I'm going wrong. But I did do something interesting. Yesterday we had basically like this fold struct, right? And we were doing fold row and fold column in the actual like process functions. So I pulled that out into an impl on fold and apply to, and it just takes an array 2 of marks, so a matrix of marks, and then it basically does the same logic that we had yesterday. So ND array is really interesting because while it may feel verbose to pick axes like this, like axis 0, axis 1, it does let us actually abstract over which axis we are operating on, which is really interesting. So up here, I choose the axes and I pull the index out of the row and the column. And that lets us use the exact same logic here for generating the ranges. So we know if we have a bug, it's a bug in both of them, right? And then the only difference between them beyond that is which side of the range they actually are applying to. So in this case, it's the left side. In this case, it's the right side. Because that's the row versus column stuff. And then we invert on whatever axis we were given. And we have the same exact logic to collect. So I think there's some strengths for ND array here, which were really interesting. Again, I'm still getting like the mangled output. So maybe I'll come back to that at some point. If I do, then I will let you all know, probably in a video on YouTube. Day 13. I guess I'll commit the steps. Why not? So all of that code is up now. And then we've got day 14. Let's do Chrome. I don't even have a Chrome window open. I've rebooted everything because I unplugged everything. Who's using? Come on. Let's choose this profile. Let's go with Advent of Code. Let's hope I'm still logged in. I am still logged in. Great, perfect. Everybody's happy. Everything's great. (14) Extended polymerization. Ooh, that axis stuff is really interesting. Yeah, so like you can write an algorithm that applies to any axis, which I find really interesting. It was really useful to figure that out and find that, and to actually write the abstraction. Okay, so we've got some submarine manual. Our input is NNCB. There are a bunch of what look like pairs. The first line is a template, the starting point of the process. So presumably we are going to pluck this off and then use that as like the start of a fold or something. Following section defines the pair insertion rules. A rule like A, B, C means that within elements when elements A and B are immediately adjacent, element C should be inserted between them. These insertions all happen simultaneously, just like the fish problem from a couple days ago. So starting with the polymer template NNCB, the first step simultaneously considers all three pairs. The first pair, NN, matches NNC, so the element C is inserted between the first N and the second N. The second pair, NC, matches the rule NCB, so element B is inserted between the N and the C. The third pair, CB, matches the rule CBH, so element H is inserted between the C and the B. Yes, think for big interactions. Iterations. Reading comprehension today is bad for me. Brute force only works for part 1. Okay, well, I'm not going to worry about that until part 2, but that is good to know. After the first step of the process, the polymer becomes NCN-BCHB. So basically what happens is one pair evolves into two pairs. And then we have this additional pair that... Do we have this additional pair that crosses the boundary? Or do we have... Then we have NC, which turns into NB and BC, and C... and CB, which turns into CH and HB. But the next iteration we need to have... We already have everything. Okay, so okay. So from one pair, we do two pairs, and then we just recursively do that, basically. Polymer grows quickly after step 5. NN, NCN. Yes, NN to NCN. But the way that I'm thinking about it is if we have to do more pair, we have to do more pair operations after this, right? So the first step is NN to NCN, right? But then we have NC and NB, which turns into NBC, and CNB, right? And then NB is BBC, BC is BHC. Do all of these have rules? I guess all of them don't have rules, do they? So NC inserts B. I guess they all have to have rules, right? Because if they didn't have rules, we would run into an error. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 7 gives us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pairs. So we get an extra 6 characters. So it's this number minus 1 times 2 is the length. And that is what, like these. So I think that's accurate. It's basically we have to treat them all as pairs and then generate more pairs. In my head, I can think of a couple ways to do this. We can either keep one string around and keep doing it, or we could do the recursive approach, and sort of unfold out until we have basically, like, we could just unfold until we have a final iterator of all of the pairs, or we could just have a string and we can just keep that string around and mutate it. So I think I'll go with the string approach first. Where is here's the test input. So let's start with the parser as usual. So parser is going to be alpha1, new line, separated list 1, separated pair. Come on, give me the little arrow thing. Where's the little arrow thing for this function? Don't need all of this. We're going to keep new line. This is going to be separated, or this isn't going to be separated. This is going to be alpha1. And we're going to return what? A string slice and a vec of string slice, right? So we need alpha1 because we're doing alpha characters. And then we need separated list 1, new line, and this is going to be separated pair with... Does the first one have to fail? Because this is going to be tag space this, right? The input is something like that, yeah. So we have... We'll do alpha1. Alpha1 tag alpha1. Is there a difference between stir and car for this problem? The problem with car is that there are 2 cars. So it would have to be, I guess, like car. which I mean is possible, right? It's basically just ease of matching later. So theoretically here we could have like another separated pair or something, or another function that just pulls in both of the individuals. But I think since we're taking the string mutable approach first, it doesn't matter. Just like real life, too many cars. That's hilarious. What's the number we need here? So we need to do to 1588. I'm not going to worry about what logic actually needs to happen there. Let's do, what is this? Initial state and operations. Is it operations? I guess it is, right? Call this rule set too. Rules probably should be a B-tree map. So let's do parsed folds dot, or yeah, parsed folds dot iter dot collect into a B-tree map of string slice to string slice. Oops, that's in the wrong spot. And that's not a reference character. Collect. There's probably something about this type that's wrong. Let's do let rules. And this will be not parsed dots, but parsed initial state. And then parsed folds is going to be something else. What is parsed folds? Parsed folds is rules, and then this is rule set. I guess it's not really a set, is it? Let's cargo test. And this is going to be a B-tree map here of the same type. B-tree map, string slice. String slice. Conversion table, yes, exactly. Does that really not work? B-tree map from rules. Vex, string slice, B-tree map from Vex, tuple of stir, not implemented for some random B-tree map. So let's pull this type in just to localize our error a little bit better. Some of these conversion functions get pretty generic, so it can help to specify exactly what we want. I did a type conversion table at the start. Yeah, you could do that for sure. And what, you just aliased it to like B-tree map or something? Why is that not working? Okay, what is the trait btree map from string slice of tuples, back of string slice tuples is not satisfied. The trait from is not implemented for btree map. I thought it was. Let's go check the btree map docs for a second. Is there a reason to choose btree map over Hashmap here? Because btree map is strictly better than Hashmap, I think. So if unless there is a reason to not have ordering, right? Unless there's a reason to specifically use Hashmap, I default to btree map. Only with a known list of items. Gotcha. The ordering is definitely nice. Let's get back to getting this. There we go. Now we have owned types. That's what we want. We are not using iter intersperse here, so I'll just get rid of that. And now our test is failing, which is what we want. Okay, so the issue here was that the tuple that was coming in was a reference, and we needed to own the tuple so that we could get at the string slices. So instead of using iter, into iter is a variant which will allow you to turn something into an iterator and get the owned types instead of the references to the types. So now we have the initial state and the rules. I'm going to call this rule set because otherwise I'm going to get super confused. And then loop, let mute. Actually, we're just going to call this state, actually. I'm going to mute a bit, make it mutable so that we can mutate it. And then we're going to loop. Actually, I don't know that this is what we want. Do we get all of the... I think we have all of the tuples, right? So like if we have NNCB and we did like a Windows on it, right? Then we would have NNCB, which would get broken apart into NC and CN, but we also need NB. So I don't think that would get broken apart into NC and CN, and then this would get broken apart into NB and BC. So I think that we always have the information we need. So we're only ever like inserting. Is there like an insert and move across in Vec? That would be a really weird function to have, I think. Like insert and push. Inserts an element at position index within the vector, shifting all elements after it to the right. So that would work. So instead of state here, we could do let mute vec equals, we have all the information we need, yes. Let mute state equals initial state dot windows 2. Is that gonna work? And this is gonna have to be like a string slice or a vec or words. Because this is a string, and we want to use windows on it, we have to do this. Yeah, unreachable expression. Oh, I double referenced it. Okay. So that's our first problem. Second problem is no method windows found for string slice. A string can be structured like a vec. String has push. That is also true. I don't think that we want to do that though, because we need to keep the pairs around. And if we construct the string, then what we would need to do is repeatedly do windows instead of inserting. I guess we would have to remove too. So that's just awkward, and we're gonna have to build up a new thing anyway. So maybe we do just keep this as a string slice, and then let state equals like empty string for now, I guess. State.clone. This will be mute. And then this will be I want to use Windows. I want to figure out how to apply slice, which I thought we had. I guess we don't technically have it. As slice dot windows 2. Method not found in string slice. Maybe I don't understand the slice type as well as I thought I did. That's possible. I thought that because we had a reference to a stir, we basically also had string slice, but I guess we don't. Coercing an array to a slice. Slices are either mutable or shared. Shared slice type is that. Clone hash. Split chunks, windows. I mean, itertools windows. That's never going to be a useful search. Iter would have slice, but it'd be cars. I think it can be. I mean, it being cars is fine. We can just reparse out into cars, right? And then check the tuples against each other for equality, or do the get with a tuple. Which is what you were saying before about, is there a benefit to doing it with tuples or benefit to doing it with cars over string slices? And the difference is how we're going to store the data and retrieve the data. So if we're going to retrieve it with tuples of cars, then we want to store it with tuples of cars because that'll make it easier for us. Tuple windows. Tuple windows. Give me tuple windows, please. Circular tuple windows. So this is going to be it for us, and then we're going to get... That's really unfortunate. I want to figure out the other stuff later, but for the moment, I'm just going to keep going. Cars, not iter. Use iter tools. Iter tools. So iter tools is a really cool crate. We haven't used it much, so I am going to use it for this instead of doing the string slice stuff. Iter tools is basically exactly what it sounds like. So if you're familiar with the iter tools crate from Python, the iter tools crate in Rust is exactly the same thing. That's docs.rs total. Let's go homepage of iter tools. So it's like basically a bunch of extra functions that you can put on iterators that are just useful, right? Some of these have made it into the Rust standard library, or at least variations of them have, but there are a ton of things here. Like we were using zip for ND array. And in this case, we could use zip on to just vex. And really the interesting thing about iter tools is it extends, so it includes what's called an extension trait, right? So iterator is a trait, and iter tools provides the iter tools trait. And the iter tools trait requires that you also implement iterator, which means that basically anything that implements iterator, as long as you bring the iter tools trait into scope, gets all of these extra functions that we see on the left here. Which is why when we go to do tuple windows, we can just do .tuple windows. And tuple windows in iter tools, so Derek was asking what's the difference between iter tools, tuple windows, and the dot windows in standard. The dot windows in standard requires that you pass in a integer to declare how big the window is, and the tuple windows in iter tools will infer that from the type of the tuple that you iterate over. So what am I doing here? Tuple windows. If we were to do something like for A, B in tuple windows, now our type errors go away, because tuple windows is reaching through that, through inference, basically, to say, oh, there's a tuple of size 2 here. I'm going to give you a tuple of size 2. Whereas the standard library Windows does not do that. This is a little bit more complicated of an implementation. I was going to show you the implementation, but the implementation is a little bit more complicated than a tuple. The implementation is a little bit more complicated than I think I want to dive into right now. Basically what this is saying is there's a function. It has a generic type T. Wow, my selection on my mouse is not doing well on Rust docs right now. Tuple windows takes a generic of type T. This means it could be anything, right? Basically, and basically the self. So it consumes self, and it returns a tuple windows with self and the type T, where self is a sized type and it implements iterator. So the iterator item type is of type T. T implements homogeneous tuple, which we're not going to get into. I don't actually know where homogeneous tuple comes from. I think it's in iter tools. It looks like it is. And it also implements clone. So from this type signature, we can basically say that it's cloning these into a tuple. The T comes through, and then there's like tuple impl, which is, I think, a whole different module. Which is why I'm not going to get into that. But basically, there's like some clever uses of traits. There's some clever uses of generics in here that basically allows us to get a tuple back instead of the windows in the standard library, and windows in the standard library gives us back an array. If I can get to the documentation. Wow, that is not useful for showing on stream. That's awkward. But you can see that in this assert equal right here, we're comparing the slice x, and this is the slice syntax right here, with a range in it. Where and this range happens to be everything. So we could potentially have done string slice, bracket dot dot, and gotten the whole thing and done windows that way. So like, let's comment that out for a second, and we might have been able to do state dot 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 windows too. I need to look up a little bit more about this because I was under the impression that the slice stuff would work on the string slices, but I'm doing something wrong, so I need to go look that up later. In any case, we have tuple windows, which works just fine for us. And then, what is this, A, B? So this is just going to be pair, right? Like we don't need to do anything with it. And we're going to do rule set dot get pair dot unwrap because it has to exist. New car equals this, and then wait, why is that complaining now? Oh, because I didn't explicitly give it a type. So what do I want to do here? It's inferring the type now. So one of the problems with generics and really generic functions like collect and this tuple windows function is that if you don't tell it what type to use, right? So we move from A to B, which is very clearly a tuple, a two-element tuple. Moved to pair. Pair is just a variable name. Like it can't infer anything from that. So it has to infer it from this B-tree map get. And the B-tree map currently is a string slice thing. So really what we want here is this. And really what we want here is pair. Not car, any car, any car. I don't think... Does that work? I've never used pair before, so that looks like it works. Rule set here then is... We want this to be a car too, because if it's not a car, then we have some problems with concatenating it and stuff. These need to match the same types, so we have car, and car. Lots of cars building a busy intersection here. It's not the trait itertools, tuple impl, tuple collect. So tuple collect is the trait that defines whether we can work with a tuple of a specific size or something like that. The thing that I just did is a little confusing at first. So we're working with type inference here, right? So tuple windows is a sufficiently generic function where if we define the type clearly in this for loop as a tuple, then tuple windows will infer that and know which tuple to return, like what length to deal with. Because we're using pair and get, if I don't include this reference, get on a B-tree map requires a reference, a shared reference to do the comparison against. So the error that we're getting here is that the trait itertools tuple impl tuple collect is not implemented for car. Sorry. So the tuple collect is not implemented for a reference to a tuple car, because this pair has to be a reference, and Rust compiler knows that. So this pair then has to be a reference. So tuple Windows has to infer a reference. When I put the reference in front of it here, we're saying that this can be an own type now, and then everything works because the tuple collect trait is not implemented on references to tuples. It's only implemented on tuples. So if that was confusing, let me know. I can dive into that a little bit more. But it is a one character fix to fix this inference. And if you're reading this error, you might not understand why. Let me just move this to the side for a second and do... I can't get this all in one line, can I? Let's do this. So I'm going to talk for a second because I'm going to turn this into a clip for TikTok. So the trait itertools tuple impl tuple collect is only implemented for references to tuples, or is only implemented for owned tuples, not references to tuples. So what we have is a reference to a tuple. Yada yada. Okay, I don't actually need to do the explanation again. I just needed the visual, and I needed it formatted in a way that I could put it on TikTok. Okay, so this runs forever because we're still looping. So we've got new car. We've got pair dot zero new car, and we've got pair dot one new car. So we're constructing the new tuples. Can we do this dot map pair car clock app stories with Chris? For those of you that are on clock app, map flatten collect string. String is weird, right? So maybe we do... because we can generate the pairs and just keep going, but we're doing the string version of it. So what we want to do here is actually format and this is going to be pair dot zero new car pair dot one. We don't need to flatten that anymore. We get this whole thing back, and then this should give us the new state. So state equals what's the problem here? Expected string slice found string. Why did we expect a string slice? Because state is a string slice up here. Is that true? We're going to toString that instead of copying it. This still runs forever. So this loop now turns into the 10 steps, I think. I think it was 10 steps, right? Yeah, I think it was. Scroll all the way down. Yay, 10 steps. For in 0.10, do this. This is going to be 0 debug state. And if we cargo test this, we get this massive thing. This is a lot. There we go. Okay, where's the beginning? They probably don't have this in the thing, do they? They don't have this in the thing. Let's just check the first few. Let's do 0.2. And let's do debug state at the beginning and one at the end. Growth goes fast? Yeah, I see that. It's exponential, isn't it? Or something like that. NCN, NBC. NCN, NBC. That's not right. NCN, NBC, CHB. I think those need to be collapsed though. So NCN, NBC, CHB, those need to be collapsed. So let's do this instead. Let's do, we're going to operate on the next one no matter what. So we can do it like this. And the only thing that is a problem, the only problem there is that we will end up without the last character. NCN, BCH, BCHB. So let's do, is there a way to tell if we're in the last iteration, I guess? NBC is a station in England. It's a station in the US too. NCN, NBC. That's like a combination of CNN, NBC, and I don't know, whatever NCN would be. Why don't we throw 9-inch nails in there too? If I can find a fair snapback and send it to you, will you wear it on stream? Yes. That's the easy answer, Xander. Like, only add pair 0 new car to the result and add at the end the last car. Yes. We just need to figure out what the last car is, which will always be the same. So we could do something really silly and do like state.iter.last.clone. Right? We could do this dot last unwrap, because it'll always be there, clone. Can we just push it after the collect? Yes. We can just push it after the collect. What was I gonna say? Let's put it this way. I am unhappy with the result of not being able to, of having just like an extra thing that we do here. If that makes sense. Like I don't like needing to last. Needing to do this little like extra thing feels wrong to me. It feels like there's a better way to do that. NCN BCHB, but it does work for us for now. So I'm just going to continue with that because sometimes it doesn't matter, like in Advent of Code. But I feel like there's a better way to write that. is what I'll say. Okay. So after step 5, it has whatever. After 10, B occurs that many times. Taking the quantity of the most common element and subtracting the quantity of the least common element. Okay, so here we have state. We'll do state dot sort. I guess can we sort on that? Can you sort a string? That would be weird, right? That's not really, it's not really like a function that you usually do. So we'll do state.cars.sorted, sorted being a function in itertools again. Itertools super useful, maybe overkill for a lot of things, especially if you're only using one function, especially if you're concerned about adding too many dependencies, getting a binary that's too big. But if you're writing a large program, itertools comes in super handy. Sometimes I wonder how much delay there actually is on the YouTube stream. Let's see. Can I do a timer? Ooh, let's do this. Let's do this. Let's do this. Get ready. Okay, get ready, because I'm going to ask you to type into chat in a second. Okay, go. I know I didn't tell you. So that's like 15 seconds. That's like a lot. I don't know how long it took Ben to realize something to type, but I know I didn't tell you what to type, and I realized that after I said go. But Ben still typed. So it's about 15 seconds for Ben, which is quite long. I didn't understand the assignment. Yes, we can do that again. Type the word test. When I'm going to click this. When I click this, I'm going to say, do it. And the next time that I say that phrase, you're going to type immediately. Do it. So really, we've got like a 5 to 10 second delay. Well, that's not too bad, actually. I am on the lowest latency. I think I'm on the lowest latency anyway. So anything more than that would be would be painful, I think. Okay, group by. Key group into iter, group by. I think we just do C, right? Do we have to count this? Dot map. C.len collect. I also find the longer I watch, the more latency gets. If I start watching on a new device, it's a few words ahead of the one I've been watching for a while. That's super interesting. Like, the way the latency works on a stream is super interesting to me. And The differences between Twitch and YouTube are mostly that YouTube streams chat in and Twitch will chunk chat in. So as soon as you type something in YouTube, I believe they send it through because their backend is kind of like implemented in a way to make it just like go. So technically a superior backend, but the experience of reading sometimes, I guess, if chat is really busy, I guess. But like Twitch will do a thing where it will chunk and jump, whereas YouTube seems to stream chat in continuously. Group data. Is that going to work? That's going to be weird, right? Oh, this is a tuple. Of course it is. Of course it's a tuple. Why wouldn't it be a tuple? Let's get this type signatures out of the way because they're a little noisy. What is the problem here? Consider giving groups a type. Car use size. Oh, right, because I didn't have collect on a type. Okay, so we have value of type car use size cannot be built from item iterator car use size. If you ever see that problem, know that you had to change it to a vec. So there are two ways to specify the type that a collect collects into. There's the kind of like average looking way here, which is like groups is of type this, and collect will know what to collect into, and collect will know what to collect into because Rust's inference is pretty good about that. The other way to do this is something called turbofish. And turbofish is what I normally use on stream, but it's this syntax right here, where we do collect, we do double colon, we open with this angle bracket, we put the type that we're using inside of these angle brackets, and then we call the collect function. The turbo.fish, I hope it is. I'm just going to go directly to it. So this is the turbofish. It's the colon with the two angle brackets, and then you call the function. It's really common. It was affectionately named by somebody on Twitter, I want to say, or maybe Reddit. Yeah, 6 years ago, why this? And somebody was like, yeah, the same with turbofish. And this is the first reference of turbofish there ever was. So this person is the reason that we call it turbofish, I suppose. Okay, so that's the groups. Let's debug the groups. This should give us the counts. 6412. We're not going fast enough or far enough, I should say, because I changed the range. So let's bump that up. And then we get 1749 and 161. Yep, those are the right numbers. So on groups, we're going to do max equals groups.iter.max by the tuple. We're going to throw away the character and do the count. Actually, this is going to be 2 elements, isn't it? So it's going to be throw away. We're going to do A and B. We're going to do A.1.comp B.1 unwrap, and this needs to be a reference because comparisons happen on references. And this is going to be the same template that we use for min. Max by key might be easier here. Is max by key a thing? Is it in iterator or itertools? Iterator probably, right? I used max by because that's what I knew in my head. Returns the element that gives the maximum value from the specified function if several elements, blah, blah, blah. Max by key x.abs. So we get to just return the values here then. So we don't have to do the comp. So you're saying that it would be like this? That looks right. I like it. Let's do this instead, though. Let's now destructure this tuple. We'll make it clear that we're throwing that away, and we have the count here. So we have max, max by key, min, min by key. I really like that, actually. Max minus min. And that's that. Max minus min can't be applied to what? What is the... Oh, right, it returns the full thing. So we'll do .1 and .1 to get the counts. Oh, meetings, but finally made it. Perfect, you're just in time for part 2. We just passed part 1, so let's go get the rest of our input. This input looks quite a bit longer, so I'm not excited about that for part 2. Why do I have foo.txt in here? Let's get rid of that. Delete. I probably copy pasted some some code from RustDoc to do file stuff. Cargo run bin part 1. So hopefully this doesn't take like ages. Let's get rid of this debug too, because the next debug for part 2 is going to be like, whoa. It's going to be real big. So let's make sure that the debug's gone. Cool. And let's see if that's the right answer for part 1. Hopefully it is. It is. And then let's do u64 max int. Okay, so we're good. We're good on numbers. This looks like a lot. So the resulting polymer isn't nearly strong enough to reinforce the sub. You'll need to run more steps of the insertion process. A total of 40 steps should do it. Yada yada. Apply 40 steps to the polymer template and find the most and least common elements in the result. You don't want to print the string from part 2. Correct. That looks like not good. I'm going to pull this out. Well, I'm not going to, yeah, I'm going to copy this whole thing because we might change this. This is the new number. What are the chances this runs? One of my attempts at part 2 overflowed U64. It was a bug in your code for sure. I'm happy it was a bug in your code and that we don't actually need U128 because I don't think U128 exists. I don't like this. I don't like this one bit. U128 exists. Fair. Yeah. I don't remember if it was U128 or I128. I can't remember. Or I couldn't remember. Target release part 2. So do the same thing as with the fishes. Okay, how do I apply the same thing as with the fishes while this is running? We're only expanding. I guess we could do references to all of the strings. So like we basically build up a vec of references to the originals. I don't remember what I did for the fishes. The fishes was... What was the fishes? The fishes was we stuck them in a vector queue and... And then we inserted each of the new... So that does work then. What I was thinking for the original part does work. Where if we have the pairs, then we can just count up in a map. So if we have NN, NC, and CB, then we can just do... does that work though? I guess we do what, like minus the NN and then plus NC and CN? And I guess that would work. So let's do it that way. In the meantime, let's see if this other one runs. So this is for 40. Initial state. This is not going to be a string anymore. This is going to be... what? B-tree map. Car. usize? B-tree map, car usize. Did I mess something up there? What am I doing wrong right there? I can put it on this side, it's fine. So we have a B-tree map car. For the record, my Neve part 2 ran for over 9 hours before I gave up on it. Okay. So maybe that won't end before stream ends. I think coding this implementation is going to be faster than waiting for that to run. Which is totally cool. So let's see. For current state, we have the counts of the originals. So we need to construct a new B-tree map, I think. Right, if we do it this way? Or at least we need to clone to do everything at the same time. Because I don't think we can do exactly what we did with the fishes. With the fishes, we just used a vector queue and we pushed them around. With the B-tree map, what we're going to end up with is a bunch of character or tuple counts, basically like pair counts. And we can't encode the count of the pair anywhere fancy. We can't encode the tuples anywhere fancy. So what we need to do is actually take the B-tree map, completely clone it, and return a new B-tree map in this state, right? So let's get the initial state going. Let's do let. Where was the Windows thing we just did? Cars lap last. You got it. Now I just need to code it. Initial state dot iter dot window tuple windows. Tuple windows dot car use size. But to do that, we have to have a new tuple, right? So tuple windows dot map. We get the tuple, and then we return the tuple in 0. It's telling me my syntax is wrong. And my syntax is wrong. Always need to remember to wrap it in the angle brackets. That's not working for some reason. Let's find out why. Method cannot be called on string slice due to unsatisfied trait bounds. What do we have as string slice? Into iter cars is what we want here, not into iter. Okay, so now we have the initial state of the B-tree map with all the counts. Well, all the counts need to be 1, I guess, but that doesn't really work for us, does it? So we need to do a for loop here instead, because we could theoretically have multiple counts. And I don't think this will add for us. So we need to do for tuple in initial state. And then we can't collect this. We're going to do just a for loop on the state as it exists. And this for loop is going to take the tuple, and it's going to do state.entry tuple .end modify v count. Let's call it count. Get a little better at using real names here. Count plus 1. And then or insert 1. Right. So either we have the entry in the B-tree map, and we modify it to be 1 higher than it is, or we insert 1. Thus, we get the state that we actually care about. So with that, we have this initialized B-tree, right? We don't really need last anymore. This rule set is going to be a thing for us for sure. I really like the entry syntax, feels really nice. Yeah, for sure. I really, really, really like the entry API. So the entry API being this, it is more of a convention than an actual like designated trait for this API, but it does allow you to do on any sort of collection that implements it. You can do .entry, and then you can choose to modify, you can choose to insert, you can choose to insert a default, you can choose to do a number of things with that entry, if it exists, if it doesn't exist, all of that kind of stuff, which is really nice. So for 40 steps, we need to take this B-tree map and we need to construct a new B-tree map, right? So let's just start with the new B-tree map. And let's say this is not going to be state equals that. It's going to be, this is going to be new state. New state is this B-tree map. For pair count in state.iter, we do need the what is it, the get here, the rule set get. Get pair, so this is our new character. And then for B-tree map, what we do is new state dot entry pair dot 0 new car dot and modify count plus equals 1 dot or insert 1. So that gives us the entries for this. I think this needs to be a reference, maybe. What's going on here? It's probably a reference that needs to be an actual value, which we can check by doing the type inlays. Again, the type inlays are amazing. Yeah, highly suggest using the type inlays. Rust Analyzer is an absolutely fantastic piece of software, and I appreciate everybody who has worked on it. Is nmodify the same thing as dereferencing the result and mutating that value? Yeah, we would have to get mute on this. And then we would also have to check to see if it existed or not to insert the right value, basically. So like we would be recreating the entry API in kind of a more verbose, error-prone way. Right, because we would have to get mute. The get mute would return a sum type or like an option type. We would have to check to make sure if that option type was existed. We would have to do the dereference plus equals 1. If it didn't exist, we would have to do the insertion of 1. So get mute and match is basically the same thing as entry and modify or insert. Okay, so that gives us the new B-tree map. We're going to return state equals new state. New state.entry or default plus equals 1. No, that is not. I don't think that's the same thing. Right. Well, I guess it is. Mute usize. So it would be. Let's check the nmodify docs. I didn't realize that returned a mutable reference to the thing. I guess that makes sense. I just don't use the entry API to grab the entry, I guess. So the entry API gives us an entry, and modify is not described here because it returns an entry struct. The entry struct, I think, has our functions, and modify returns the entry. So everything returns the entry, or insert. Okay, so or insert returns a mutable reference to the value. So in this way, you can do like an entry, and then if you wanted to do more mutation with it, for whatever reason, you could guarantee that you had a value here when you did that, when you got it. So yes, same thing. I prefer, so not actually the same thing. So let me explain why this is not the same thing. What we're doing here is we're getting the entry, right? And if it doesn't exist, we're inserting 1. What we get back here is the value 1 if we didn't have an entry, right? So if we do plus equals on that, this can only be set to 2, right? The result of this expression right here is that we set it to the number 2 because we insert 1 and then we add 1. So n modify will do the thing irrespective of or insert, right? So if it exists, we modify it or we insert it, right? It guarantees that we do one or the other, but not both. Whereas the dereferencing, that or insert 0 would be the same, yeah. So, I mean, it depends on what your logic, like what logic you want to be. In our case, it wouldn't be the same if you or insert. But if you're going to or insert 0, you can or default. Right, so there's or default here, and the default for number types for usize is 0. What does or insert with key? Ensures a value is in the entry by inserting, if empty, the result of the default function. This method allows for generating key-derived values for insertion by providing the default function a reference to the key that was moved during the entry key method call. This reference to the moved key is provided so that cloning or copying the key is unnecessary, unlike or insert with. So if we have expensive keys, we might want to do or insert with key, which will give us a reference to the key, it looks like. So we can derive a value off the key without actually having to clone it around, kind of thing. That's cool. I didn't know that existed. But yeah, so we're in the B tree map, and we have the pair counts. We have the, let's get rid of this dereference that we don't need anymore. We have the pair counts. We're incrementing. I think this does everything, right? Except for the fact that this is the counts, right? So pair count. We need to call this something else. This is count. So this is not going to be plus equals 1. This is going to be plus equals pair count. And then we're also going to or insert pair count. So now we get a little bit more complicated, right? And now we go, if you're using zeros and ones, it's easy to differentiate between or insert and modify and the dereferencing. But in this case, if we have a value, we want to add pair count. If we don't have a value, then we want to insert pair count, because that will produce the number of pairs that are in that count. So does this build? Cars, so these are still wrong down here. We still need to do this operation though. Can we do this operation with the way that we've done this? right? Because I don't know. I'm just going to assume that it works out for a second. So B tree map will give us the pair and the pair count. So how do we, there's an open question here about how we get the value that we need at the end, I think, that I wasn't thinking about. So that builds. It seems to run quickly. So how do we do the count here? Right? Debug state. Debug state. So we have a bunch of pairs, right? And we have the counts of them. So we know how many, theoretically, we know how many of each of these we have, but we don't have the actual count, right? So let me cargo run this on the test data instead of the and see what numbers we get here. We have 2 of each letter in the pair minus the first and last ones. That explanation does not compute in my head, Derek. So for like this, you're saying just double it? Half it. Half it because when we're doing the insertion, we're taking that n and we're making an extra n. That makes sense. Because when I was talking about how long it was going to be, it was the length minus, what was it? Length minus 1 over 2? Or something like that. The math working out like that is not at all intuitive to me, but what happens when we have, so here's a question for all the people in chat that are saying just half it. What happens when we have odd numbers? Right? If we have H and H, and we have like whatever 2 bajillion 559 for H. We have that. I guess. Let's check. Yeah, that halves to 0.5, right? So do we need to add them all up and then have them? Yeah, I'll add them all up and then have them. Because, anyway. So let's do state.iter.map. What is it? Tuple AB count. A count. B count. What did I mess up? There's a syntax error. I'm not writing JavaScript. This is not a fat arrow function. That's what I messed up. This is going to be call expression requires function. Expected function, which I thought we have. Let's do this. Expected function. Why is this expecting a function? We have the map arguments. And let's give it a little bit more syntax here just to call expression requires function. Is it thinking count is a It's not a question about even a count for BB means two times the count for B. Okay, but Commander, I don't understand if you're saying specifically the fact that there are two Bs means that we should double it, or oh, need a comma. You're right. Thank you. Commander, I don't understand if you're talking about specifically that tuple has two Bs in it, therefore we need to double it, which is, for me, an obvious statement, or if we need to double it because what we're doing is we're duplicating them as we go up and we're duplicating the pairs, basically. In which case, that number for B is actually the correct number for that B, right? We don't actually need to... It's not a 2x count for B in that spot if we are doubling them as we're doing it. Because if we halve and half, then we get that number. Borrowed here after move. Right. This... for C count in this, then we just build up the B tree map ourselves. You're grouping it as pairs, so BP count 2x count for B. You said the same thing twice. Right? For that state, that entry C dot or insert count. Dot and modify VV plus equals count. Right. This is just car. This is just car. Those are what? Expected car found tuple. Why is this a tuple? do we get that for free? That's cool. Is that? And then this is C count? No, that's not correct. Changes the counting from pair counts to single car count. To be clear, count the single car from the beginning. Isn't that what I'm doing? I'm building up the counts in the B tree map. Let me just do this for a second. A count state is a B tree. That's why I was messing up. State.iter flat map A B okay, expected use size, found reference to use size, so we put this in like that, right? Or did I mess up? Expected tuple, this is new state. Right now I'm just dealing with my naming. My naming is not the best right now. Okay, so we should end up with new state here. We get these values. These values are the wrong values. B needs to be probably half of that. So let's do that thing. That's still an odd number. New state dot iter dot for thing in, and we're gonna debug thing over 2. $209. That's not the right number. I think we also need to add the first and the last cars, which should solve the odd number thing. Y'all have to be more specific when you type messages in the chat, yo. So we need to keep the last character around here, which we are already doing because it becomes a pair. Right? So in part 1, we had to do this character because we were collecting into a string. And we were only inserting the first pair, but we're inserting both pairs now. In the above example, the most common element is B and the least common element is H. Subtracting these produces that number. Yes. Change the counting from pair counts to single car count. Isn't that what I did? Thing plus 1 over 2. 209,556 is still not the right number. How many digits are in this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's the delay for me. Text is coming very late. Yes, totally understand. One more to just the count of the initial first and last characters. The first and last characters of the entire string. We don't have the first and the last characters though. And also plus 1 is not enough to bring this up to the right number. 384,987. Sure. But if I add 1 to the first and the last car, that doesn't fix the count for B. So, right, like we can still do this, which is what y'all are talking about. Initial state dot iter let mute it equals this, it dot next dot unwrap let first car equals this, let last car equals it dot last dot unwrap, and we do what, new state, same thing, right? We grab this. If for whatever reason it's not in there, it gets 1. If it is in there, it gets added 1. And this is first car. And then we do the same thing again for last car. So this is what y'all are talking about, right? Which is fine, right? But doesn't solve our problem. The counts here are not there's something about the counts duplicating, but we're not actually. I feel like we need to maintain the count as we build up. If we don't maintain the count as we build up, then we are not going to be able to get the count data from just a list of pairs. The over 2 logic is faulty? I don't think. Like, it's thing over 2 or whatever, but the thing over 2 is not the count, right? counts we get are way up here. They're almost double what we should have, approximately. That one's 4x what we should have. Like, if we do over 4, I think C gets closer. Oh, iterate over all the pairs and increment the count for the first one in that pair. That... Does that make sense? Because the one that was added is always the second one, so the first one is technically always a thing. So we shouldn't be flat mapping here. I'm just going to comment this out. We should dot map AB count a count account. I'm an accountant. And then this, and then did we do over? I changed it to over 4 for no reason. And that doesn't give me the values anyway. So that is also the wrong count. I think we have to build the count up while we're doing the fold, y'all. I don't think we can get the count from just the pairs. Show without. This is without. Right here. Let me make it bigger so you can see. This is the count without. I'll run it again just to be sure. But this is the count without. How are you accounting for the pairs that are not pairs after the insert? They're just removed, right? We're building up a completely new B tree. We build up a completely new B tree every time, Derek. So any of the pairs that were in the old B tree are not in the new B tree. We have to build the count up while we're doing this. There's no other way. You did the count at the end and it worked? Okay, I would like to see your code then, because I don't see how the math works out in that way. Because if we have... Let's look at the test input just for a second. If we do this, right? We've got 2 N's and a CB. So here we have 2 N's, 2 C's, 2 B's, and an H. So if we have only the pairs, then we have NC, and we have CN, and then we have NB. So we have 3 of these. So we incremented N by 1 by holding pairs, even though, actually we have NC, CN, NB. Yeah. We incremented N by 1 without actually having more N's. So if I could think of the, whatever algorithm that is, the growth, then we could reverse engineer it, I guess, but I don't know that there is one. Because it's, I guess there are rules, right? But also, we would have to know those rules beforehand. Unless this is actually like perfectly fit for some algorithm and I'm not aware of it. But that would just be like a problem setup thing. Like they set it up so that this would work. And they didn't say anything about it. So we have to do the counts. If we don't do the counts on the way, then we can't. DMU solution on Discord so you can check it out at your leisure. Appreciate it. Where's part 2? Part 2. State counts. The counts for these initial counts are correct. Well, it's not correct actually. So let's do for car in, or for C in initial init eal state dot cars counts dot entry C dot and modify v plus equals 1 or insert 1. So this is our counts, and this is going to be the thing that we use for the new car. So that keeps our counts, and then here we do counts. Actually, we don't do this whole thing, do we? Because we have the individual character counts now. So, and we don't need this, because we have those already. So if we run this now, on part 2, which is doing the test input, that seems low. Did I not put this in? Like, we only do one character insert here, right? So what did I just do wrong? I'm missing something really obvious. Initial state.cars, the cars go in here. This will count up to like 3 or whatever. So let's debug that just to do checks. We're just checking. Making sure that we don't run off the rails here. So 112, right? BCN, which is accurate. BCNN. Let's do after one step. 2212. 2212. Yep. So those counts are correct. So for the 40 steps for the test input, we should be getting numbers that are way higher than that, right? That's what I'm doing. I'm only counting the character from the insertion commander right here. So on every step, when we build up this B tree, we're only inserting for each new character. That produces some absurdly low number for some reason. because I'm not adding the pair counts. So the pair counts aren't actually what we need. Is it pair count? Am I supposed to be adding pair count? I think that's exactly the same number we got earlier. There's something else very wrong here. The same wrong numbers, yes. Exactly. I don't Y'all are sure this approach works? Because y'all were saying this logic works earlier. Hopefully, yeah, okay, that goes up on the other screen. So think logic. What are we doing step by step for counting, and what are we counting? Okay, I'll do that before I look at Derek's code, before I cheat. Oh no, that's my Rust adventure list of stuff that I'm working on. Ignore that. You never saw that. Don't worry about it. It's a very long list of a lot of stuff. Okay, so new state is the next state. So it's all of the pairs from the last one plus the counts, right? So each of the counts, new state is a new counter for each round. Yes. If new state is a new counter for each round, right? So we're counting the same thing that we were counting before, is basically what that means. Right? So pair count isn't actually what we want. Brain breaking. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It's still, I mean, the count is low, right? The count for B needs to be 1, 2, 3, 4, 5, 6, 7, 8, 9. The count for B needs to be 100. Or is 9 billion? 9 zeros. 1 billion. Yes. 2, 3, 4, 5, 6, 7, 8, 9. So we need 100 billion Bs. We're missing 100 billion Bs. But we are... State is what? State is the original count of the pairs. So it's like... Oh, you know what? Do we need... State has to be the counter for the pairs of the first state of the starting loop. It is the counter of the first pairs of the state of the starting loop. Right? Initial state cars, tuple windows, that takes each pair that plus equals ones or inserts one. So this is the count, right? If we debug, where are we debugging counts? This is part 2. Where is the count debug? Nowhere. Okay, let's do debug counts and state, right? If we debug counts and state, counts is 112 and state is CB, NC, and N, right? I'm not mutating the state in a step. I'm returning a whole new state. Think of this. You insert pair 0 new car. The second one is pair 1 new car. And the second one needs to be new car pair 1. Oh no. Is that what I did? Oh, thank you. Oh, thank you. Thank you, thank you, thank you. I appreciate you, Commander. Oh my god. Nothing wrong with the logic. Just a simple case of I put them in the wrong order. Rough. Absolutely rough. So I'm curious to know if this works then down here. I really appreciate the point out of that, Commander. That was a frustrating one. Okay, where's new counts? New counts. And there we do the 301, 73, 53. So all of these numbers are correct except for B for some reason. If we iterate over this like this. Is there a B at the end of the original one? There is a B at the end of the original one. But N is correct. The B is the very, very last character, yes. So maybe we need to do... This is better than before? Yes, it's definitely better than before. I would like to remove the counting of them as we go up and do the counting on the pairs. So I'm going to figure out why... Oh, because we removed this one. Right? So if we do this instead... Right? Which is the original thing that I did. Then the new counts. New counts. New counts are still wrong, but then we get the first and the last one, which is what we had last time. So we'll stick with map. And the reason we need the last one is because we cut the... Is because why? Why do we need the last one? I get that we need the last one, but I don't understand why we need the last one. Because I thought we accounted for the last B in the very initial count. let's get rid of the new count stuff for a second, and we'll finish this out and make sure that we have the right answer, and then we'll go back and we'll fix it. 219.602.73 384.987 73. So we need to do the max and the mins. And this is on counts right now. And counts is going to be, what is counts going to be? Counts is character count, which should be this, right? Oh, do I need a deref? I need a deref. And then this is the answer. .218 ends in 29, 218 ends in 29. So this is correct now. We can take this out and do input, and we can run it. H is not in the starting and is correct counted. You cut the right one out in the pair counting, the last B will be left off as you're counting, since it'll always be a right element in a pair. But I count the B in the beginning, right, Derek? Is that true? Did I do that in the counts? Puzzle input, yada yada, part 2, counts, entry C. This is .cars, which means that we, at the beginning, when we count, we have it. So this is the answer. Let's submit this. Huzzah, we have the right answer. Thank you for pointing out that typo, Commander. That was a really frustrating typo to have. So if we go back and we check the test stuff, right? And we look at the count when we start off. When we start, B has 1. So we're not missing a count for B, which is my confusion, right? Oh, no. Okay, so when we do the pairs one in the new counts, then it's missing. I was mixing up the initialization logic between counts and the other one. So if we do all of this, and then we get down here and we start doing new counts again, then the thing that we have to do, counts iter map, this a count, because B is always the last one, and we're chopping B off here, then we need to pick up B again. Just gotta throw this right in there. And then let's get rid of this because that doesn't exist anymore. And if we run this again, we get type errors because I messed up. So now what we have is this thing, which I'm doing over 2 for no reason at this point. 602, 301, 73, and 53. .602, 73. That looks right to me. So let's uncomment these maxes. And then we will... Is this new counts? It's new counts. Okay, so then we just add the B on the end, and we end up with 218 and 29, which is the right answer. So this is the way that we would do it with the count. Yikes, that was let that be a lesson to I don't know what that's a lesson for. Make sure you don't typo on stream. Do these tests actually run now? These tests actually run now. Heap, clear, part 1 dat. What I really need is a way to run dat and automatically insert dat and criterion into this README. That's what I really need. I bet you that's a totally like writable thing. Like that's totally a thing that could like cargo test doc or something like that would do it. Okay, there's that and there's that. And then let's get rid of these debugs. I'm iterating over that. I probably should rerun this because I just took an iter out. Actually, that looks exactly the same, doesn't it? 27818, 205, yep. Non-parser for dat output readme? Maybe. Maybe. Am I into this? Cargo bench. And then we run it. I'll need to compare your part 2 to my part 2 because there's still a bunch less than mine. Did you do the same thing I did? I didn't actually look at yours yet. I thought you did the same thing. But if not, that's interesting, for sure. Four milliseconds and 400 nanoseconds. I did it pretty similar. Yeah, that's the vibe that I got from what you were saying earlier. 482, so like, we'll call it 500. I think in nanoseconds, we can do that. Is there anything we can do here to like change this? I think part 1 is pretty hefty, but part 1, we're building everything up in a long string, so I don't know that we really need to look at part 1 much for the dat heap, because when it comes down to it, what we're doing is a lot of allocation. Actually, that might be the it might be, and this grows pretty fast, right? If somehow, actually, we do know how big this is going to be, right? We know exactly how big this is. Let me I'm actually, hang on, I'm excited about this. We know exactly how big this is going to be. Actually, we know the max size vec or whatever that we need. And actually, we know all of the vecs for all of the sizes ahead of time. Does it take less memory if you use Hashmap instead of btreemap? We can test that first because that seems pretty easy to test. Let's do all of them. Let's just Hashmap. It takes 1 kilobyte-ish less. It takes, the TG max is ever so slightly more by like 100 bytes. The total usage is ever so slightly less at 500 kilobytes-ish. So there's a slight difference between Hashmap and btreemap, but there is not a big difference for part 1 anyway. For part 2, using a Hashmap doubles the total usage. It brings our TG max down ever so slightly, but it doubles the total heap. I committed this already, right? No, I didn't. I should do that before making too many changes. I think btreemap is the right default choice. Unless you specifically need a Hashmap for some reason, I think btreemap in Rust is the right default choice. Let's just readme day 14. Push that up before we change too much other stuff. And then I'm going to take this Hashmap change out. Yes, I can do that. Cargo bench with the Hashmaps. I actually don't know. I assume that because btreemaps are sorted, this will be slower with a Hashmap. It's all good. 3.8 milliseconds. And what was the original? It's basically the same, 3.8 versus 4.1. And slightly higher on... So in the spot where we're... In the place where we are using the btreemap more, right? I think in part 1 we don't use it as much. In part 1, we do a btreemap for the rule set, and that's about it, right? We don't use a btreemap for anything else. So the change there is just from a single initialization of a Hashmap or a btreemap. In that case, the btreemap seems to be bigger than the Hashmap. Nikki, I did it. It's fine. It's a simple change. But where we use the Hashmap extensively, and where we use the btreemap extensively, it provides a benefit over Hashmap just by default. My guess in part one, it's more efficient because the order doesn't matter. Part one is less efficient in general. And it's also because, Derek, that we're not actually inserting anything. If you notice, for part one, the only B tree map we have is the rule set that we collect from nom. And then we do a bunch of string initialization, basically. Okay, what was I going to do? I was going to initialize like a string with indexes, right? Do B tree maps have more efficient inserts? Great question. Let's go check. Because we can check this in the Rust docs, I believe. So I want to show how to do that. There was recently a issue raised on Twitter, is the way that I'll put it, about potentially improving the like big O notation of how these things work. So B trees represent a fundamental compromise between cache efficiency and actually minimizing the amount of work performed in a search. In theory, a binary search tree is the optimal choice for a sorted map, as a perfectly balanced binary search tree performs the theoretical minimum amount of comparisons necessary to find an element. So this is for searching for the element. However, in practice, the way this is done is very inefficient for modern computer architectures. In particular, every element is stored in its own individually heap allocated node. This means that every single insertion triggers a heap allocation for a binary search tree. And every comparison should be a cache miss. Since these things are both notably expensive things to do in practice, cache misses are expensive, and heap allocation is expensive, we are forced to at very least reconsider the BS tree strategy. So a B tree is like the next generation of BSTs, I suppose. You could consider it. I don't see anything in here about the insertions. It's really only about searching. It is a logic error for a key to be modified in such a way that the key's ordering relative to any other key, as determined by ORD, changes while it is in the map. So as long as you're not trying to do that. I don't see anything about B-tree insertions, though. We might be able to find it on Wikipedia. What's the backing structure for the Hashmap? SIMD lookup on Hashmaps. Interesting. Quadratic probing. I don't know what quadratic probing actually is. The hashing algorithm. There are other hash maps in existence with different hashing algorithms. I don't see anything about inserts, actually. I don't see anything about the performance here. So that might be something interesting. Rust performance B-tree map Hashmap. I don't think that the insertion performance is usually... This is just copied from the docs. So this is the Rustlang users forum, which if you are into Rust and you haven't discovered this yet, users.rustlang.org. It's actually super useful as a thing that you can search through and find conversations that other people have had in the past about different topics. I often actually go through here just to figure out like what people are having trouble with and stuff like that. Why did Saturday JSON and Toml both decide to use btreemap rather than Hashmap? btreemap is significantly faster than Hashmap for many of the benchmarks in JSON benchmark. The Reddit article said for min-max operations, btreemap is quicker. Yes, because it's sorted. Or are you not referring to like getting the max value or whatever? I guess that would be the max key value anyway. But generally, a btreemap is a nice safe default for Saturday JSON value. It's nice to have map entries serialized in a predictable, sorted order. So yeah, I don't know what the insertion complex like. I don't know. I assume that btree probably has like there are really interesting data structures here too, but insertion, and it depends on the algorithm that's used, and I don't know which algorithm is used. So for the most part, it won't matter for us. So it's probably kind of a huge rabbit hole for stream. Thanks for diving into it. Yeah, I mean, like, I thought this was going to be talked about in the docs, actually. So I thought we were going to be able to go to the docs and it was going to talk about the insertion algorithm used in the btreemap. To be honest, the insertion algorithm of a btreemap versus the insertion algorithm of a Hashmap has literally never mattered to me at all. Like, that has never been a thing that I've needed to think about. Not for practical industrial purposes is the way that I will phrase that, right? It has never mattered to me in like writing a serverless function or CLI application or something like that. But I also don't write like, I don't necessarily write high performance like file scanning like ACK or ripgrep or something like that. So take it for what it's worth. So yeah, I mean, it depends which production implementation of a btree, because there's like, once we start getting into data structures, right? There's binary trees, there's B trees, there's B plus trees, there's something else. I think I have something on my own GitHub that's a B tree. Wow, that's a big, that's me, right there. I am actually taller than that door, yes, for those people that are wondering. R star tree is what I was thinking of, actually. Because that's 9 years ago, I was doing the Hilbert R star tree is a really interesting Hilbert R star tree. I should look that up again. So the reason I was thinking about this was the Hilbert R tree is an extension to B plus trees, which we were just talking about B trees, which come from binary search trees. And I think R star is an extension to the Hilbert R tree. So like once you start getting into like these data structures, there's a lot of them and they do a lot of different kinds of things, which is really interesting. And I find it really interesting, but I hate when people ask interview questions about them. That's the way I'll put that. I really like looking at data structures and like whatever. historically, choosing the right data structure at the level of Hilbert R tree versus Hilbert R star tree has never mattered for me. Not really. I don't do low level database indexing work or something like that. So, but choosing like a set versus a vec is probably a more relevant example of data structures, like choosing your data structure well, like a vec versus a B tree or something like that. So anyway, that's a dive into B trees and B tree maps and stuff like that. The lesson here is use B tree map by default unless you have a good reason to use a hash map. Let's see. A B tree map knows where data set is. A hash map needs to compute to find the data. Yes, totally. Chris can't do that TikTok sound 6 foot tall and super strong because he's too tall. Yeah, I mean, the people that are doing that are not 6 foot tall. So I don't think it matters. I'm too get off my lawn to get that reference. What should I Google to get it? I don't remember what I said, Nikki. For every problem, there is a special data structure to solve it. There is a lot of benefit in reframing is what okay, so the way that I'll put this is there's a lot of benefit in reframing the way that you think about how your program operates from a series of steps into a set of data structure transformations. And this is the key to unlocking things like functional programming and the iterator chains that people find very confusing often, right? Things like fold and reduce, things like even map, right? And then the higher level, more complex versions of those things like scan and whatnot. Thinking in data structures and how the data structures are going to flow through your application leads to you having to do less individual little bitty work. So if you've ever done something like index into an array and do like an I+2 or whatever to get the right index, there are better ways to do things like that, right? So for example, if we need the first item in an iterator, we can use .first on the iterator. If we need something that is the last thing in the iterator, we can use .last. And that extends to doing these iterator chains and reframing your mind to think in the data structure flow and how you store your data. Because if you store your data correctly, your program logic can be simpler, right? If you store it, and a very simple or a very small example of this is if you store a bunch of values in a vec or an array versus storing them in a map or a B tree map, right? For a vec, if you want to go find a value, you have to iterate through the entire vec to go find whichever one that is, if it exists, right? In a B tree map, we don't have to iterate through the entire vec if we already know what the key is, right? We just go directly to the value that we need. So in that way, choosing the right data structures on a very granular level is a really important thing. But choosing data structures on a very minuscule level, where it's like getting into the Hilbert R star tree, like B plus tree versus whatever kind of stuff, becomes less important. So one thing that I did want to check is we know how big these strings have to be. Specifically, very specifically. So if we do all of this stuff, right? And we do let new state equals string with capacity, we should, based on the length of the current string over 2, right? No, is it over 2? There's an algorithm here. I was thinking about it earlier. So we know how big these are going to get. A 4 goes into 7. So 4 over 2 plus 1, right? 2, 3, 4, 5, 6, 7. 7 over 2 is going to come down to 3, plus 1 is 4, right? Oh, thank you. I still managed to not make a TikTok because I know if I'll do, I'll spend too much time on it. Yeah, that does happen to TikTok. 1, 2, 3, 4, 5, 6, 7. 4, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 4, 7, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So 4, 7, 13, 25 is what I said. So 4, 7, 13, 25, right? So 2x minus 1 is the next one. 2x minus 1, 2x minus 1. Yeah. So state that length times 2 minus 1 is the string that we need to create. So instead of doing what we're doing here with the cars, we can initialize that string, right? And then move it out at the end. So this is going to be the last character. Wait, did I do this in the right spot? I did do it in the last spot. Okay, cool. New state, state.cars, right? We're iterating over it. We're doing tuple windows. We get the new car rule set, right? Here we're formatting this, but we don't actually need to do that. So we're going to get rid of this push. Well, can we just push these all on? Right? So instead of formatting this in, we do new state.push pair.0 and new state.push new car. Right? So we've allocated the string already. And we don't need this. And this gets to be for pair in this. Get rid of this map because we're not doing a map and a collect anymore. And then new state.push last, right? And then state equals new state. And I'm curious, first of all, if that produces the right answer. So this is only for part 1. We got 3009. And by allocating the right sized string, we brought the allocation down to 200 kilobytes over 470. And then for kicks, we'll run a cargo bench to see what that does. What time is it? Okay, we're good. I need like a clock up there somewhere. Maybe a clock app. Okay, so Our runtime for part 1 was what? 4.1 milliseconds. And our runtime now for part 1, because we've pre-allocated these strings, is almost 2 seconds. So all we've done here is we have, based on the size that we think the next one is going to be, we have predicted the string size and initialized it with the proper capacity, which is the previous 1 times 2 minus 1. And by using that and mutating it and pushing these characters onto it, we have ensured that this string never needs to grow to accommodate exactly the size of the characters that we actually need. And in that way, what we've done is we've taken it from 469 kilobytes for our total heap allocation, all the way down to 222. So we've roughly halved our total heap allocation just by knowing how much data we actually need to allocate and not letting Rust expand every time we insert a character. Because we're inserting very small pieces of data, right? We're inserting individual characters. So we will hit the barrier more often because we're doing very small inserts into this string. So pre-allocating actually saves us a lot of bumping the size of that, because strings are growable, right? Capital S string can grow. So if we hit the edge of the size that a string has allocated, it needs to grow again, and thus we need to allocate all of that space. So because we're not doing all of those extra allocations, we've actually brought the runtime down too. So those allocations were taking us an extra 2 milliseconds to handle. So just by knowing how much data we are actually going to use, we've improved the total memory usage and performance of our application. Note that our TG max went down slightly, but not too much. 138 to 152. Yeah, totally, Nikki. Always happy. Never feel like you have to hold questions back just because I'm talking about something. I'm always happy to, if I don't cover it, go back and cover it. And if I cover it, then I covered it, and we're good. It's definitely cool that today's and Sunday's problems both had places where I got to use pre-allocation to improve some heap stuff. Yeah, for sure. I think that's really cool. I'm actually wondering if there's any more we can do. We haven't actually looked at, so we do 10 strings basically here, right? Dat heap view. I need this like in my bookmarks bar or something. This is such an absolutely useful website. I really appreciate this person for hosting it. Okay, so total, let's say 163. That's the wrong dat heap. Day 10. We're not in day 10. We are in day 14. .heap.json. Okay, so 222, that sounds better. That all goes down to what? Are these our strings? 12 bytes is probably the file open. 20 bytes might be our first string. Process part 1. 2 owned with capacity. Looks like a vec. Looks like our parsing. Then in process part 1 on line 45, 45 is our string. So anytime we see this 45, we are allocating one of those strings. This is in puzzle input. So this is collecting into the B tree map, which is only 144 bytes, 240 bytes to puzzle input again for the B tree map. I wonder if we can allocate, or like we can size this B tree map to 600 bytes to the B tree map again, a kilobyte to printing to standard out. Iter tools, 40 kilobytes for sorting our iterator. So keep that in mind. 40 kilobytes for sorting our iterator. B-tree maps don't let you presize them? Interesting. I didn't know that. B-tree map. Reserves capacity in a collection for the given number of additional elements. Looks like there's a nightly API to do it. Range, pop, length. Drain filter, contain key. New. Does not allocate anything on its own. Interesting. So if you do a new B-tree map, you allocate nothing. And then I guess you allocate every insert if you need to. That's the only way to extend them though. There's not a way to create it with a given size. I don't see a way to create it with a given size. I also don't have a concept for where the data is stored in when using the B-tree map. And it doesn't tell us whether it stores data on the heap or not in the docs. So I think we would have to look at the source to figure that out. I have the thought that it does, but I don't know for sure. I think there was a Rust forum course on why you don't need to do it. Cool. What was I talking about? The heap. 136 kilobytes to sorting. Again. This is 57. This is this sort. This sort is a lot. Is this the same sort? That's the same sort. We do 2 gigantic allocations for sorting that. I wonder if we need to. This is group by, right? So maybe we don't need to group. Maybe there's something that is more optimal. Counts. Counts gives us a hash map. Do we need to collect here? We just get counts then, right? Cars counts. What is the type of groups now? Hashmap car usize. Iter, max by key, count. And this is an option? Why is that an option? Does it return? Oh, it returns an option. Never mind. Car usize. So these are copy. So dereferencing them will just copy them. So hopefully this works. Wow. Look at that. Look at that improvement. by using .counts instead of .group by we are down to 46 kilobytes total. Did everybody see what I did there? We basically had this thing here that was doing a sort and a group by and an into iter and some other stuff. And then we were collecting it back into the groups. But by using the write function, or in this case, the write function being counts, which already does what we want to on these cars, right? And counts lives in iter tools. So another usage of iter tools that is very cool. Because we use the write function, we are actually don't have to build up all of those intermediary data structures anymore. Let mute counts equals, so it creates a new hash map and inserts into it for each one, which is the code that I would have written if we were going to write this manually. So basically for each whatever, insert into a hash map. I probably would have used a B-tree map just because we're using B-tree maps, but using the write function, especially on a high level like this doesn't take us code to write, really. It's just saying, give me the count of everything. Brought us down an additional, 180 kilobytes? It's a lot. Can it run part 2? Can what run part 2, specifically? I don't think we have... I don't think we have that available to us because we're storing the counts, right? So .counts works on the other one because also remember that part 2 only runs in 42 kilobytes. So by using .counts, we're almost at 42 kilobytes here. Or I guess we went down to brain fart. We're only at 27 kilobytes in part 2. Right? Like we never allocated all of this stuff in part 2. The things that we changed in part 1 are we pre-allocated all of the strings that we were building up, which we are not building up anymore. And we changed our iterator to be more efficient, right? To use .counts. So we predicted the sizing of the strings and pre-allocated the strings, and then we used .counts, which is a hash map insert, instead of doing a bunch of cloning in our iterator. And that's what brought it all down. So I think for part 2, if we were going to work on it, we really haven't finished with part 1 yet. I guess we are finished. There's not much more to do. We had some huge wins. I don't know that there's more to do here. This is just iterating over groups. This is just iterating over groups. Like we can take a look at the heap profile because we just ran it. But we just took out the vast majority of what we were allocating. Actually, we should do the cargo bench too. Let's do cargo bench. It's significantly smaller on the heap, but is it faster? I mean, my guess is yes, it's significantly smaller. In general, if you reduce allocations, you probably get a faster program, especially if you're doing a ton of them. So now we're running in 1 millisecond. Right? Part 1 now runs in 1 millisecond, which is about double part 2. So we can be done with part 1. I don't know that there's much else to do. We have to allocate these strings to do this. We might be able to take the part 2 approach and apply it to part 1 and then not do the string capacities here. Right? Because we're just doing the same counts. And the part 2 thing that we did is more efficient. It's exponential, so I'm guessing it's still too slow. What is still too slow? Oh, the original part 2, like the part 1 algorithm in part 2 is still running. Like we started it over an hour ago, probably. But we have a more efficient algorithm for part 2 here, right? So if we copy paste this into part 1, it's the same thing, right? I think it's the same thing. And then this is 10. So if we run that on part 1, that gives us 25 kilobytes. Right? So, I mean, we get huge wins out of changing to use the part 2 version of it. And that would have been like the right move to do. And then bench takes us. I should have been committing these the whole way. I didn't commit these, did I? So what did we get? 127 nanoseconds. So like we did what we would have needed to do if we were trying just to absolutely like improve everything for part 1. But I think it's interesting to look at what is actually taking the space and then improve that little by little, because sometimes you do have to write it the other way, right? So being able to debug what your heap allocations are, understanding why they reduce, understanding what that does to the runtime, having the benchmarks to prove that it's done that to the runtime, are all really important things, right? So this is 25 kilobytes, right? And this is 27. So it makes me feel like anything that we do from here on out is going to be in the nom parser and not in the function that we are actually running. Can I just replace this for a second so that we have the old version? This is the old version, right? Counts, yes. Yikes. Okay. Did I just save that in day 12? What did I just... What? 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 That's annoying. This is now the day 12. Let's get rid of that. Let's drop this back in here. Okay, so this is GAU part 2 algo or part 1. Git push, git stash, because we don't actually care about, well, let's do rm // day 12 lib.rs because I pushed the wrong button. And then, yeah, so that's what I'm thinking for part 2. I think we've optimized the B tree about about as good as we're going to optimize it. The only other thing that I can think of is we're generating a new B tree every single time. We could modify the numbers instead. I don't know that it's worth it. That probably is a decent amount of our heap. Let's do the DAT for part 2. And then if we refresh this and we look at the DAT for part 2, then we're looking at 7,000 kilobytes for the B tree. This is all B tree again. So the B tree allocating a whole bunch. And then we go down to 469 bytes for the next biggest thing. So this is all B tree allocation. Basically all of the heap in our program right now is B tree allocation. $130, $130, $130, and it's all at $130. So what's line 130? This B tree allocation. This one is all apparently this one is always the one that forces the allocations to happen. But this is where we have all of our heap in. So I don't maybe there's a better way to represent this. We're basically constructing a single B tree map that counts. So actually, so we construct the new B tree map and then we replace the old one. So if we did subtraction here and stuff instead, maybe it would work. I still think that this is going to be rough. Wonder if we could do it in one tree by setting the count of new state.entry pair equals 0. Maybe. I think that if we set up the B tree here, right? And then we start modifying it here inside of the iterator, I think we run into mutation issues. Because we could potentially be inserting new items into the iterator while we're iterating over it. But maybe we can... I don't know. I bet you there's a way to do it. I think that I am done with this problem for today. I'm not going to keep running this part 2. I'm going to kill that as soon as I can. But yeah, so we did a bunch of heap stuff today. I'm really happy with how once we solved the problem, we were able to bring down the heap, bring the runtime down. I think that was really interesting. Yeah, use the right data structures. But that's it for today. I need to get some water, get some food. Same time tomorrow to do day 15. I appreciate y'all hanging out.